All right, so last time in class we started our example with M&M's for exponential decay function. And I told you guys I would finish it for you today in class to help you out in the calculator method of finding the best fitting equation. So what I'm going to do is I'm going to go through and I'm going to use the numbers that I put on the board here. 152, 78, 36, 20, 11, 5, and 3. I just made these guys up. Yours would have been somewhere close to this probably if we got to finish our experiment last time, but we didn't get to finish that. So I'm just going to use these numbers as my y values in my table. So in order to find the best fitting line on the calculator, remember the key to that whole process was to use, first of all, this stat menu. And so when you push stat and you go to edit, you have the ability to enter in your list 1 and your list 2 from your table that's on your sheet over here. So when we type these in, you can type in the number of trials here for your x value 0, 1, 2, 3, 4, 5, and 6, making sure that you hit enter each time as you type these guys into the calculator. Then we want to go through and enter our y values from our list. You can see those over on the side of the page here. And so we'll enter in 152, 78, 36, 20, 11, 5, and 3. And so now that we've got them entered into the calculator, remember I told you, you enter them into the stat menu on the calculator. You also want to go to stat plot, which is above the y equals screen, to plot these points. So you hit second, hit the y equals button, and it takes you to stat plots. Make sure that it is turned on. Some of them will be turned on at sometimes if you're using my calculators in class, unless I have cleared them, which they probably will have been cleared before you get to this class. So make sure you turn it on. Click enter, go to that on and highlight it, and hit enter again. And now the points are plotted in my calculator. So once the points are plotted, then I want to go to graph to look at them. The problem is my graph is usually not set up to where I can see it. So in order to see all of those points correctly here, remember you go to zoom and then you go to the one that says zoom stat. So when I click on zoom stat, then it zooms in on those points that I have in the stat menu of my calculator. So you go to enter the points in at stat, you go to stat plot to plot the points, and you go to zoom stat to zoom in on the points. You should see that this has our characteristic shape of an exponential function. This one is exponential decay because it's going down, it's decreasing, which should make sense because your number of M&Ms should have decreased each time that we did this. So then what I want to do is I want to find the exponential best fitting equation. So I go back to stat, click over to calculate, and then I can go down the list here and find the one that stands for exponential. Remember, when we're looking at this, just like we did before earlier in the year when we did the linear ones, we want to choose the one that is appropriate. This is exponential regression line, which is the same thing as a best fitting exponential line. So we click on enter, click one more time, and it will bring up on the screen for us a times b raised to the x power, and it will give us what a is and it will give us what b is. In other words, it's telling us that our function, our beginning amount, is 146.47, and inside our parentheses, raised to our power, the b to the x power, like we talked about in class, our rate and things like that, is 0.517, or we can round that to 0.52. In other words, this is an exponential decay function because this right here is less than 1 because it's 1 minus the rate that we see here of 0.52. So that means my rate would actually have to be 48% in order to get 52 here, because it would be 0.48 when I move my decimal place over to give me 1 minus 0.48, which is 0.52. So that's telling me that my M&Ms are decreasing by basically pretty close to a half. if you think about the fact that we had the ones with the m we counted and the ones without the m we ate, that is why it's decreasing by half, because you got a 50-50 shot of getting an m or not getting an m. So this is my beginning amount, and inside my parentheses there. Same thing that we did last class when we were looking at all those values of cars and values of bank accounts and things. This was just talking about M&Ms. I'm going to do another one of these with you so you can see that process in the calculator one more time. This one is the African black rhino population. This table, it's kind of hard to see probably, but I'm going to tell you the years are 1960, 1980, 1991, and 1992. The population is in thousands, so it's 100, 15, 3.5, and 2.4, which is 100,000, 15,000, 3,500, and 2,400. But we're going to use these decimals here like they are, because that'll be a little bit easier for us than typing in 100,000. Also, what we're going to do over here for the years is we're going to change it up a little bit. Instead of using 1960 for our number in our table, we're going to use 0 for 1960, which means 1980 is going to be 20, 1991 is going to be 31, and 1992 is going to be 32. So when we go to our calculator to type these things in, just like we did before, we go to the Stat menu, go to Edit, and we go over here to List 1. If you want to, you can delete things individually from there by hitting the Delete button, or you can actually clear the whole list if you highlight L1 at the top up here and then hit Clear and then press Enter. It will clear the whole list. So we're going to type in our X values of 0, 20 for 1980, 31 for 1991, and 32 for 1992. Then we're going to come over here and we're going to do the same thing over on this side, except we're using our population of our African black rhinos. Push Clear, enter the list here of 100 for 1960, 15 for 1980, 3.5 for 1991, and 2.4 for 1992. So again, we've entered these guys into our list just like we did before on the other one. So we've got it into our Stat menu. Since we already did the other one and we go to Second and Stat Plot, our plots should already be turned on. That has not changed because we did not change previously from the previous problem. So then we go back to Graph, but now I still can't see my points. This is what's going to change if you change from one graph to another. You still have to go back to Zoom again and go down to Zoom Stat in order to zoom in on those points. This one's going to be kind of hard to see because you got one up here at 0, 100, this one at 15 and 20 and 15. And then you got 31 and 3.5 and 32 and 2.4. So they're way down here. So it's kind of stretched out, but that is an exponential decay function. It has a curve to it. I know some of you could probably argue that linear would also kind of work for this one, and it kind of would. But exponential decay is going to be a little better. So we go back to our Stat menu again, go over to Calculate, and we can find our best fitting line by going down to EXP, REG for exponential regression line, or best fitting exponential function. Press Enter, enter one more time, and then we've got our exponential function here. 110.54 is our beginning amount. In our parentheses, we've got 0.89 raised to the x power. That's our b to the x power. Because what's happening is it looks like 11% because 1 minus the rate is 0.89. That means my r would have to be 0.11 or 11%. So this thing is going down by 11% per year. It looks like it's more when you first look at the table, but if you look at it over actual time, there's 20 years in between here. That's a big jump. So that's why it drops so much from 100 to 15. But it's really going about 11% per year is what this population is dropping by. So there's my function with my beginning amount and my 1 minus r inside the parentheses. Okay, what I'm going to do with you now is I'm going to review a couple questions with you that are going to help you on your quiz. Your quiz is going to involve your properties of exponents like we did with our little booklet. And then it is also going to involve a couple of those exponential growth and decay functions. and probably a little bit of calculator work with the best fitting equations, just like we just did just a second ago. So let's start with a couple properties of exponent problems. Let's start with a couple easy ones, and then we'll work our way to a little bit harder problems. So one of the problems that we did was something that looked like this guy right here. Let's say we have 6x to the second power times y, and we raise that to the third power. Everything in the parentheses is going to be raised to the third power, because when you have a multiplication problem inside parentheses and you raise it to a power, you can just raise everything. Remember, you can't do that with addition or subtraction, but you can with multiplication or division. So I can raise 6 to the third power, and that's going to give me 216 when I multiply that out using my calculator if I can't do it in my head. Then I have x squared raised to the third power. Here's where you have to remember another property. When you raise a power to a power, you multiply. So what's 2 times 3? It's 6. So that would be x to the 6th power. Then you raise the y to the third power. And so you just bring those down beside the 216, and that's all you can do. There are no like bases to multiply. That is all you can do to simplify that. So that would be considered simplified. And so on the first problems on the quiz, that's what you're going to be doing, is simplifying using some of these properties of exponents. Okay, so let's look at a couple more. Let's say you are multiplying like bases. Something like x to the 6th times x to the 7th times x to the negative 3rd. You can take this piece by piece, or you can do it all at once. It doesn't matter to me, just as long as you use the properties of exponents. So we're multiplying like bases. So when you multiply like bases, what do? You add the exponents together. So you do 6 plus 7, that would be x to the 13th power. And then you do 13 plus negative 3. Be careful there. 13 plus negative 3 is 10, so it's x to the 10th power. Some of you can do that all at once. You can do 6 plus 7 is 13. 13 plus negative 3 is 10, and go straight down to this answer. That's fine. And then there are a few of you who will say, well, Mr. Harrison, can't I just take that negative exponent and move it down to the bottom? So I'd have x to the 6th, x to the 7th, and then move that down to the bottom and have x to the positive 3rd on the bottom. And that's absolutely fine. That would give you x to the 13th over x to the 3rd, which is 13 minus 3, because you divide like bases, you subtract the exponents. 13 minus 3 is 10. And so you would still end up with the exact same answer no matter which method you use. As long as you are using the properties, you will be fine. So since I mentioned it in this problem, I will go and talk about one of those negative exponent problems, because one of those is usually ones that get people a lot. So let's take a look at this guy. Let's say you have negative 2y raised to the negative 5th power. When you have a negative exponent like that, what I told you to do is move it to the opposite part of the fraction and make it positive. So when you have this, basically what happens is this becomes 1 over negative 2y raised to the 5th power. You basically, like I said, move it to the opposite part of the fraction and make the exponent positive. Don't do anything to the base, just make the exponent positive. Because what I can do now is actually do both of these things to the 5th power. Negative 2 to the 5th power and y to the 5th power. Negative 2 to the 5th power is going to be negative 32, and y to the 5th power is sitting there beside it. Now, let's take a look at probably one of the more difficult problems that we do in this section. Let's say you have something like 2xy over 3x squared y to the 2nd, and you raise that to the 2nd power, and then you multiply that whole thing by another ugly fraction of, let's say, 16 x to the 5th, y to the 7th over 2x to the 1st, y times z Just beautiful, right? Well, let's take it and let's break it down piece by piece. First of all, let's look at this first parentheses because that whole parentheses is being squared. So you need to square everything in this parentheses. So that means you take the 2 and you square it. 2 squared is going to give you 4. So if you want to go ahead and write 4, that's fine. X squared on the top is x squared. Y squared on the top is y squared. Don't overcomplicate it. If they don't have an exponent already, you don't have to worry too much. On the bottom, it gets a little trickier because 3 squared, that's pretty easy, that's 9. X squared already has an exponent though. So when you have an exponent raised to another exponent, you multiply them. So what's 2 times 2? It's x to the 4th. 2 times 2, y to the 4th. So I have this big ugly fraction multiplied by this big ugly fraction over here. So when I have that, usually what I'm going to do is I'm going to multiply straight across the top, straight across the bottom, and then I'm going to try to simplify any division properties that I may have. So 4 times 16 is going to be 64. X squared times x to the 5th is x to the 7th. 2 plus 5, like we talked about in that other page. Y squared times y to the 7th is y to the 9th. Then we put this over 9 times 2, which is 18. X to the 4th times x to the 1st is x to the 5th. Y to the 4th times y to the 1st is y to the 5th. And the z is just kind of hanging out down there. Now what we can do is we can divide and see if there's anything that this simplifies to. If you can't divide 64 by 18 in your head, remember the calculator can always help you reduce fractions. If you do 64 divided by 18, it's going to give you a decimal that you can push math, enter, enter, and change it back to a fraction of 32 over 9. In other words, you divide both of those by 2 because they are both divisible by 2. Then you can divide like bases with your exponents here. 7 minus 5, because when you divide like bases you subtract, so that's x squared. The reason it's on the top is because the 7 is the bigger one on the top. Y to the 9th, y to the 5th, 9 minus 5 is y to the 4th, because the bigger one's on top, it stays on top. And then the z on the bottom does not have a like base on the top, so basically you just leave 9z on the bottom there. Okay, so now we're going to take a look at a couple of examples of our exponential growth and decay functions. And you've already turned in your homework, so I'll look at a couple off your homework here to help you out, to give you a little bit of review off of that as well. I know you don't have your homework sitting in front of you anymore, but this will at least help you out in reviewing for this quiz. So we've had some things like bank accounts that we've talked about. Okay, so let's talk about a deposit of $1,300. This is the first one off your homework. It says you have a bank account that pays 4% interest yearly. Okay, so 4% interest. Remember we talked about this. This would be really good. Most bank accounts are not going to give you that much. You're probably going to have to find something a little more along the lines of investments to get this type of interest. So we're going to use it though because it's part of our homework. Let's first of all write what the function would look like. And this is going to help you out because if on the quiz I ask you to write a function, you better be able to literally write the function, not just type the numbers in your calculator. Yes, that's part of it, but I want you also to be able to know what the function looks like so you can always write that function. So our function is going to be y equals, remember this is a growth problem, so we're going to have our beginning amount of 1,300. And in our parentheses, like we talked about when we were doing that example with the M&Ms, in our parentheses, we're going to have our 1 plus the rate of 4%. Don't forget to move your decimal place 2 places over, and so you should get 0.04, and you raise it to the t power. Notice in this example so far, I haven't even talked about the time, because when you are writing a function, you do not actually plug in a time. You write the function with variables still involved here and here. You could also use x here if you wanted to instead of t. That's okay. We typically use t because we're most of the time talking about time. So when we look at this, This would be our function, $1,300 times 1.04 to the t power. So if we wanted to find the amount after a couple of different years, in your homework you had 3 years for one of them, then you had 6 years for another, you had a couple more, but I'm just going to do these two right here. You would take this function now. You still got to know the function, but you take it and you type it into your calculator exactly like it looks. Your parentheses beside that 1,300, 1.04, and you raise it to the power, but this time you're actually going to plug in your power of 3 years. You get $1,462.32. So when you're looking at this, I am expecting you to be able to round correctly for money. If you don't, you will miss points. Since we're using the same function, we can hit second, enter, and it pops it right back up on the screen again. And if I want to find the value after 6 years, I just take and replace that 3 with a 6. And I get $1,644.91. So $1,644.91. So you can also use exponential growth and decay functions when we're talking about things decreasing in value. One of the examples that we had on our homework was a population of a city that was decreasing. So it says between 1970 and 2000, the population of the city decreased by approximately 2% each year. So it's a 2% decrease. And when you look at that, it says in 1970, the beginning amount was 600,000 people. Okay? So if you are finding the function for this one, it's going to be 600,000 as your beginning amount. But in your parentheses, it's going to change up a little bit. You're going to have 1 minus 0.02. Because this is decreasing. This number that is inside this parentheses is going to be 0.98 raised to the t power, because this is going to be going down each year. So 98% of your population is left after each year. 2% is gone. So that's why 0.98 is what is left there in that parentheses. So then when you want to find the population after a certain number of years, then you can just plug in the number of years here. So for this population, it said the year 2000. Well, if 1970 was the beginning, the year 2000 is 30 years later. So if I want to find the population after 30 years, I take 600,000, type it into my calculator. Remember, it's 0.98 because it is decreasing. And then we will take this and raise this to the 30th power. And that's 30 years later. Their population is 327,290.5, right? Or 0.6. Wrong. Do not round people to decimals. Doesn't matter how short they are, they're still a whole person. Okay? So even if they're missing their legs or missing half their brain, they're still a whole person. So when you round people, make sure that you round this to 327,291 people. Round it to a whole number. More than likely, if you were reading some type of magazine article or a newspaper article and they were talking about the population of a town decreasing like this, they would probably even round to maybe the thousandths place or the hundredths place. But it's okay with me. You round to the whole number spot. That's what I'm looking for. Don't round to 2 decimal places like you would with money. So basically, guys, that is the stuff that is on your quiz. So if you can go through and you can do those properties of exponents, you can deal with the exponential growth and decay functions that we have done and the things that we've done in the calculator with those, you will be fine on this quiz. So, have a great day. Finish your quiz. Do well on it. And then I'll see you guys next time in class.